was hard to decide where to begin with this class. There's not really a clear beginning point in what we need to talk about. So I decided to jump right in with some of my favorite sayings. And what I just pulled up here on the shared screen is the standards for mathematical practice. And this will be in one of your first reading assignments, and we'll be talking about these over and over throughout the semester. And as you read about them, I have actually never seen any other reading assignment describe the whole look for and make use of structure standard the way that I'm going to describe it. Over the years, I have developed my own understanding of what this really means. And so let me tell you a little bit of a background story on how I came to develop some of my favorite sayings. Okay, I've never done a research study in education, and I wouldn't want to be honest with you. But what I have done over the years is I've informally studied what makes students learn, right? What confuses students? What are the best practices? And I have the opportunity to see a lot of lessons because I supervise student teachers. So I get to see a lot of really lousy lessons, which are actually great learning experiences for everyone because then I get to help the candidate fix them. And I have lots and lots of anecdotal evidence for what I think makes students struggle to understand mathematics. So I don't have stone cold hard data like a research study would produce, but I do consider myself an informal researcher of what are the stumbling blocks that make students struggle to understand mathematics. All right, and so I want to kind of share some of my main thoughts on that topic with you right off the bat. So anyway, when I mentioned seeing not so great lessons and how that's a great learning experience, I was in a classroom many years ago at this point, watching a student teacher teach. And so, the topics on the board, right? That this is our learning target of the day, simplifying and multiplying radicals. And so she began the lesson like this, right? Here's radical 50. Okay. And so she taught the students to factor it out. If we weren't living in a world where students abuse calculators, they'd probably have an easier time seeing that that's 25 times 2, right? But not all students can do that because of overuse of calculators. So she had them break that down into its factors. And then she used that cute little saying, which that if you have a pair, if it has a partner, it comes outside as 1. Okay, and so she said, okay, class, today we're going to simplify radicals. This is what you do, and here's the answer. And students had their calculators on their desk from something they had been doing previously. And so a student raised their hand and said, I just put this in on my calculator and it's the same answer. And the student was completely confused, right? They said, I typed it in my calculator, radical 50. I got like 7 point something. I typed in 5 radical 2. I also got 7 point something. So they're the same. And yet the student thought that didn't make sense. All right. And so that was a pivotal moment for me in understanding the way that students think. And it made me realize how students think that math is not supposed to make any sense whatsoever. Because think about what this student was expecting. This student was expecting that he was going to start with radical 50, and then we're going to come up to radical 50, and we're going to just change it. I mean, what would we change it to? Right? But he thought you should come up to radical 50, change it, and somehow get a different answer, and then that would have made sense to him. All right. So it made me realize how students expect to come to math class and not have anything make any sense at all. Okay. So that was one eye-opening moment for me. And then something else happened in this same lesson. Okay. In this same lesson, because she was multiplying radicals. So she taught the students, that if you have radical 2 times radical 3, right? And then you just multiply them, and then it's radical 6. And then if you can, you would simplify it, right? And the students were pretty happy at this point. They were saying, oh, wow, that, this isn't very hard. This is easy. Okay, we're all happy. So they did a bunch of practice problems, and then they start working on their homework. And on their homework, there was a problem like this, right? And so this student teacher realized that everyone was calling that radical 7. And so she reconvened the class and said, oh, listen, everyone's getting this one wrong. Listen, the rule I just taught you, it doesn't work for adding. And you could almost see just how dejected it was, like sort of sucking the air out of all these poor students. Some of them who were going along happily and, oh, I get it, I understand it. All of a sudden we're just like, what? And there was no explanation really for it. It was just, oh yeah, this rule I just taught you, well, it's only for multiplying, it's not for adding. And students were kind of frustrated, and then it just became, yeah. So, if you see adding, you can't use the rule. Can't use it. It only works in multiplying. So again, when I tried to talk to the student about what went wrong, the student teacher, what was wrong with all of this? This understanding of the difference between multiplying and adding became something that I realized needs emphasis. And so I see this as part of the difference between adding and multiplying. I see part of this as part of looking for and making use of structure. There's a certain structure to when we add anything, whether it's radicals, expressions in algebra, fractions, whole numbers, right? There's a certain structure of always needing like terms. Okay, so this paragraph here, I encourage you to write this down. So to add anything, I must have like terms or units, like units. But to multiply anything, I never need like units. Because here's the problem. Students think that math is like hundreds and hundreds of different rules. And it's not. There's a few rules that we need to watch out for. Okay, and this is one of the rules that is a common thread from whole numbers right on up through, college level mathematics. Then here's the other rules that I want to argue much of math boils down to the use of these rules up here. Okay, how do I change the appearance without changing the value? And this was one of the phrases that I told this student teacher that she should be using. Okay, because that student was so confused that radical 50 and 5 radical 2 had the same value. All right, but they should have known from the beginning of the lesson that what she was doing was changing the appearance, but not the value. I suggested that she compare this to reducing fractions, right? It's sort of the same idea. We're just taking an expression and we're writing it in another form. Because one thing that I have learned over the years is students don't understand equality, right? And you probably think that sounds weird, right? But what they don't really understand is how if two expressions are equal, that means we can substitute one for another anytime we want to. We can always substitute something for its equal. And think about how much we do that in math, all right? And that's part of the structure of math. So anyway, I talked to this student about changing the appearance without changing the value. And just answered this part. One of the things we can do is substitute anything for its equal. Okay, because we had that cute little saying, and you'll see me when you watch my video where I'm teaching this lesson to my pre-calc students, you'll see me say that as well. But you'll also notice that I start this lesson by asking students what this is, right? I start off by saying, what's radical 5 times 5? Okay, it's 5. right? And so what I'm doing here is I'm replacing something with its equal. So there's that cute little saying of if it has a partner, it comes outside. That's fine. That's sort of a cute way to remember that. But this equals 5, right? I am going to replace it with its equal, right? That's how to describe what I'm doing in precise mathematical terms. All right, so what else do we do in math if we want to change the appearance without changing the value? All right, we multiply by what? And I tell every class that I have ever taught, I make them write this down. And they roll their eyes at me and they think it's ridiculous because they think they already know this. And yet students, many of the mistakes students make are because they don't apply these things to their work. All right, because what is it that I can multiply by if I want to just change the appearance without changing the value, right? What's the answer to that, right? And all of you know it's 1, all right? But remember that 1 comes in many forms, right? That's 1, that's 1. Right, so think about how often we multiply by 1. We don't even realize it. But if I want to add fractions, right, if I'm adding something like this, what I'm doing, the reason this is legal is because I take each fraction and I multiply it by 1. If I multiply by 1, that's how I know the appearance changed, but not the value. Okay, I still have the same value because each fraction was multiplied by 1. I use this a lot when I'm explaining to students why their work is wrong. And so when they sit down with me in my office and they say, I don't understand what I'm doing wrong, I'll say to them, well, did you do one of our legal things? For example, a student might be working with an expression like this in Calc 1. And they know the radical is a problem. So I'll say, okay, well, what do you think you should do? And they'll say, how about I square it? How about I take that expression and square it? Right? And then I bring them back to this and say, well, is that on our list of legal things to do? Would that change the appearance, but not the value? Right? And then they say, oh, wait, no, okay, I can't square it. Right? And so then I lead them to, they're going to want to multiply by the conjugate. And again, sometimes students will do this. Oh yeah, multiply by the conjugate. Okay, well, again, did I do one of my legal things? Did I just multiply by 1? I didn't, right? Not until I do this as well, right? Now I've multiplied by 1. Now I know that I'm changing the appearance, but not the value. Okay, so that's something I say over and over in my classes. Change the appearance, but not the value, right? Or substitute anything for its equal. I actually said in one of my classes, so I had a student once, I think she took 2 classes with me and then she was a TA for me. And so I will often say, if you want to be a good mathematician, you just have to be a good substituter. And so she got me a water bottle. It was probably my favorite gift that I've ever gotten. It was a water bottle. So you know how you get those like coffee cups or water bottles and it's got a quote on it, it's maybe quoting like Winston Churchill or somebody like that. So it was the quote that said, if you want to be a good mathematician, you just have to be a good substituter. And then my name at the bottom by Erin Harris. So that was one of my favorite gifts ever because I say that so many times. Down here under what else we can do for add, we can add 0. And we don't really see that quite as often. I think we definitely multiply by 1 more often than we add 0, but completing the square is somewhere where we add 0. Okay, and then how else? So this is where I'm talking about an expression, right? What if I have an equation, right? Then what are legal things that I can do? And anything that we do to an equation is not wrong if we maintain the balance of that equation. So I can maintain the balance of an equation by, right, doing the same thing to both sides. And there is a little caveat here, like if I square both sides, I add an extra an extraneous solution or the potential of an extraneous solution. So there is a little caveat there. But for the most part, if I'm working with an equation, right, as long as I do the same thing on both sides, I'm not wrong. I'm going to talk a lot in your class about the benefit of wrong answers. And I just asked one of my student teachers, where have you used a wrong answer as a learning experience? Okay, she was doing this equation in 8th grade. She asked the student how they wanted to solve it, and the student said, add 10 to both sides, right? And she said, okay, I'll add 10 to both sides. And then she said, okay, am I wrong? Is this wrong? Right? Well, it's not wrong, right? Because you didn't disturb the balance of the equation, right? That equation is still in balance. The problem is it didn't get you any closer to your goal of isolating the variable, right? But that was a great place for her to promote this idea that, you know, it's not wrong if I've kept it in balance, but, you know, it didn't lead me to my goal. And this is a great example of using a wrong answer as a learning experience. So, as I said, I don't think students understand equality. And I don't think students see this type of structure as far as a common rule for adding, a common rule for multiplying, and then the structure in multiplying by 1, possibly adding 0. We do that a little bit less. If I were president, I clipped this example from Math 140, Math Concepts for Elementary Teachers. I make those students do problems like this, but if I were president, I think we need a lot more of these types of exercises at a young age, right? Which are nice concrete examples. We're going to talk a lot in class about going concrete to abstract, right? Starting with this nice concrete example where I say, okay, everywhere that I have a star or a heart, I can replace it with 2 smiley faces. Right now, everywhere that I have a star, these are in balance. I can replace any star. Every single star then can get replaced with 4 smileys, right? And that's how I keep this in balance. Okay, so I would do this for every one of the stars. So personally, I think we need a lot more of these types of problems at a young age for students to help them understand equality, help them understand maintaining the balance in an equation, right? And help them understand I can substitute anything for their equal. So the next thing you're going to do is you're going to watch a video where I go through this in detail. And then I'm going to have you watch my lesson from pre-calc on exponents. And there's also work in there or on radicals, and there's also work with exponents, fractional and negative exponents. One of the things I want to point out to you is how often I compare and contrast. All right, that is also one of my favorite teaching techniques. And I tell my student teachers, if you don't compare and contrast at least once a day, something is wrong. But the longer I've been teaching, the more I've gained an appreciation for the compare and contrast strategy. So honestly, in this probably about 15-minute video, I feel like I have just thrown a ton of information at you. But I wanted to start the class right off with talking about some of the things that I think are very fundamental to helping to develop math students who can understand that there is some structure to math. All right, it's not just all these totally random rules. All right, when I've talked to students over the years, they talk about, yeah, math is all these rules, and then if you forget your rules, you're in trouble. And I'm not big on trying to convince math students to memorize rules. All right, and as you watch some of my video clips that I'm going to assign you from pre-calc, you'll probably see places where I say, I don't want you to memorize this. I want you to know where it came from. All right, so let me end this segment here, and I'll let you go on and watch a couple of these things that I have preached here. I want to let you watch me put those into action.